Hello all. We will be discussing assignment 2 this time. So as usual, we will go over one question at a time and we will see the solutions. Question 1. Inline assembly refers to interspersing a C program with a block of assembly code to carry out a particular operation. So this by definition is true and hence the answer is true. Question 2. The assembly translation of a C function with a void return type does not contain the RET instruction. So the purpose of the RET instruction is once RET executes, the address of the next instruction which was stored in the stack is retrieved and placed in EIP. So the purpose of RET is to carry out something more basic, that is to return to EIP the return address of where it must go back. Let's say there is a function call and you call the function here. RET in this function gets EIP back to this next instruction. So that is the function of RET and hence this is false. Question 3. In the following C code, statement 1 does not translate to any assembly statements. So as we know, hash define, until hash define is called in the program, it does not translate to any assembly code. So this statement, if you try and work it out, if you try compiling it in the C compiler, you will see that this does not translate to any assembly code. Only when this statement is encountered, it translates to an assembly code which is equivalent to num into num. So this is true. Question 4. Statement 4 returns the value stored in the address py plus 4. So py is of the type int, right? So star py is the value in the address pointed to by py. So let's say py points to some location in the memory here. So star py is this value, and whenever you do star of px, let's say star py plus 1, so let's say this value is for example 2, so star py plus 1 is 3, right? So that is how this statement works, and hence statement 4 returns the value stored in the address py plus 4 is wrong. It returns the value stored in the address py and it increments it it increments it by 1. So the value for in this example is 3. So this is wrong. So hence it is false. Statement 5. Question 5. Statement 3 stores 0 in the address pointed to by px plus 4. Px plus 4. So let's look at statement 3. So star of px plus 1. So what is the difference between this and this? So this is value in the address px plus 1. So since px is of the type int, right? Px is of the type int. This statement px plus 1, the C statement, this C statement translates to px plus 4. So let's say if px was char and we do plus 1, the C statement is px plus 1, it translates to px plus 1 in assembly. If px was int, px plus 1 translates to px plus 4, and if it was double, px plus 1 translate to px plus 8. So using this logic, this is true. Let's look at question 6. The value present in the C variable y after statement 5 executes is 300. Okay, so let's look at what is happening here. Swap 2 comma 300 is the function which is being called. Swap is a function and the arguments are 2 and 300. So x is equal to 2 and y is equal to 300. So temp is equal to 300 in this statement, y equal to 2, so y equal to x, right? So y equal to 2 and x is equal to temp, right? So return of x, so return 300. So the value present in the C variable y after statement 5 executes is, so this is statement 5, after this executes y is equal to 2 and hence 300 is wrong, so hence it is false, right? The value present in the C variable a after statement 12 executes is 300. So after statement 12, so once statement 12 completes its execution, what is a? So return 300, right? So 300 is returned, so now a is equal to 300, hence the answer is true. Okay. Now let's move on to section 2. Let's go to question 8. What is the value in the register EAX after the execution of statement 5? So what is statement 5 here? XOR of EAX comma EAX. Okay, for let's take an example. EAX is 3. So in binary 3 is 1 1, right? So XOR of EAX comma EAX. Let's look at what this is, what is happening here. Let's say XOR of 1 1 comma 1 1, we know it is 0. So how so to like explain this, let's look at the truth table of XOR. Let's say the inputs are a and b and the output is y. So 0 0 0 1 1 0 1 1, the outputs are 0 1 1 and 0. So when you look at this yellow color boxes, whenever a equal to b, right, that time y is equal to 0. So based on that, whenever you do when you perform XOR of the same variable eax comma eax, the same register, this happens, this is basically a bitwise operation. So XOR of the same variable results in 0 and hence eax is equal to 0. How many times does statement 7 get executed in the above code? Statement 7. Okay, so let's look at this. EAX is 0. We know that from this previous discussion. ECX is equal to 4 because of move ECX comma Y. Now add EAX comma X. That is the first time LBL is executed. That is statement 7. So EAX becomes 3 now. After that, again ECX is decremented. Now what was ECX? It was 4. Now it goes to 3, then to 2, then to 1. So when jump 0 LBL, so whenever jump not equal to 0, jump not equal to 0 LBL. So until ECX is not equal to 0, it will keep going back to LBL, and hence we can see here that ECX is not going to 0. It's finally going to 0 over here. So statement 7 executes 4 times, right? Okay, so let's go to question 10. What is the value stored in the variable z after the execution of the above code? Variable z, right? So let's look at what is EAX. When this statement 7 executes 4 times, add EAX comma X, what happens is EAX was initially 0. It is first added with 3 and then another 3 and then another 3 and then another 3, which in total is 12, which is now moved into Z in line 10. Z, it's moved into Z, right? So Z is equal to 12. Okay, so now let's look at question 11. Which C statement can be removed so as to maintain the same assembly code obtained when compiled for maximum optimization? Okay, so let's look at how this question is approached. So when you look at what is returning from a function, return R, right? So whatever anything pertaining to the computation of R cannot be removed. So everything which is related to R needs to remain. So in this case, R equal to A percent S from here, and A is computed using X plus Y, S is computed using A minus Z. So we need this, this and this. But Q is not used anywhere in R. Hence, Q can be removed. Q equal to A by S. This statement can be removed. Hence, statement 6 can be removed. Now, let's look at question 12. In statement 8, if statement 8 was changed to return Q, then which C statement can be removed so as to maintain the same assembly code obtained when compiled for maximum optimization? Okay, so again, we will look at it using this similar approach. Let's say 8 was replaced by return Q. Now Q is equal to A by S, and A is equal to X plus Y, S is equal to A minus Z. Hence, this statement, which is R is equal to A percent H S, let's use pink. Okay, R is equal to A percent S is not used in the return statement, which is statement 8. Hence, this statement 7 can be removed. If statement 5 was changed to S is equal to X plus Y and return Q, and statement 8 was changed to return Q, then which of the following C code will result in the same assembly code when compiled for maximum optimization? Okay. So this obviously is basically S is equal to X plus Y and return Q. This is the exact modification that is prescribed in the question. This will be, which of the following C code will result in the same assembly code? So this will result in the same assembly code. Okay. So now let's look at other options. When you compile this given set of this given, when you compile this function using the prescribed compiler, which is MSVC 19.0 with maximum optimization, you will find out that this also gives you the same assembly output. This also gives you the same assembly output. But what you need to look at carefully is that does the compiler account for this corner case where X plus Y equal to 0? So though these two give you the same assembly output, the compiler has not actually cared for these corner cases. So these do not result, these two options do not result in the exact same output, as the compiler has not cared for the corner cases, and if cared so, the assembly output would be different. Hence option 2 is the only correct answer, and this option is wrong, as it is S is equal to X minus Y instead of X plus Y. So this option is wrong. The other three options might look option 1 and 3 might look correct, but they are not correct. Only option 2 is correct, as the corner case as X plus Y equal to 0 is not checked for in option 1 and 3 in the compiled assembly output. Question 14. After the execution of the following code snippet, what is the value by which the pointer variables PA and PB are incremented respectively? So as we saw earlier, whenever whenever PA is equal to PA plus 1 and let's say PA is char, then the assembly output increments it by 1. If it is int, it increments by 4. If it is double, it is 8. So when we look at this, PA is char and PB is double. Hence 1 comma 8 is the right answer. Moving on to question 15. In which statement of the above assembly code does the C variable count get initialized? Okay, let's look at if the C variable count is initialized in any of the statements here. So we can see that in none of the statements this variable count is even initialized, right? So this seen in the assembly code output that it does not allocate any memory for the C variable count, and hence this is the right answer. What is the corresponding assembly statement that performs the operation of the C statement return count? So we know that by default value in EAX is the return value. Hence the value in the register EAX is treated as the return value of the function. Is the right answer. Question 17. The functionality of statement 5 in the above compiled assembly code is to compare the value in the address ASP-4 with the character /0, right? So when we look at statement 5, what it's doing is basically this, right? So it's basically comparing if the value in the value in ECX is equal to 0, and hence this is true. What is the value of EAX after the execution of statement 13 in the assembly code? Statement 13. Statement 13 is return 0. So once it returns, what is the value of EAX, right? Now, since this assembly code is only showing the function strlenfn, you need a calling function to call this function and pass PA. So only when PA is passed, we will be able to determine what is the value of EAX. Hence, the answer is depends on the number of characters in the string pointed to by PA. So moving on to question 19. In statements 4 and 5, the address of the C variable A and B are loaded into the register EAX. So what is happening here? X is the address, Y is the address of variables A, B respectively. So that is what is happening, and hence the answer is true. Question 20. What is the value in the C variable A after statement 8 executes? So what is statement 8? Pop of EAX. So let's look at what is happening here. Push value in the address EAX. So what is EAX? Let's say AB in the actual memory is this 2 and 300. Now the address of this is passed to EAX. Address of this is passed to EBX. Now push EAX pushes 2 into the stack and then 300 into the stack. Now in this address location, which is this and this respectively in statements 8 and 9, pop of EAX and pop of EBX. So first pop returns 300, and that is put into this first address location pointed to by EAX, which is X. And the second pop operation, let's say in pink, that is 2, that pushes 2 into this address location Y or B, just 2. So finally in the addresses, finally the variables A and B have 300 and 2 respectively, right? So the answer here is 300. What? And what is the value in the C variable B? That is 2, right? 2. That is the so we are done with this session, and I'm your TA Balaji. So any doubts can be taken up in the forum. Thank you very much.